Okay. Hi everyone. Thank you all for coming to the final SEEC Toolbox Seminar for 2019. We've had a bunch of interesting talks this year, so that's been great. And to end off, we've got David Marqueza and Rose Elstead speaking today on dynamic occupancy models. Both are core members in SEEC. David is also an honorary research member of SEEC and employed by Sandy, and his interests lie in conservation of grasslands in the eastern area of South Africa. Rez is the director of SEEC and associate professor in the stats department here, and his interests lie in the intersection between ecology and statistics, with a focus on demography, population and community ecology, and species range dynamics. So thank you guys very much for speaking today.
Thank you, Bianca. Yeah, so what we're going to do is I'm going to first give you an introduction and overview of the dynamic occupancy models. I'm going to use some simulated data, and then David is going to do the more interesting thing with a real data set, and it's going to show you an example of where we use dynamic occupancy models. Okay, so if you're going to use dynamic occupancy models, it's really important that you first are comfortable with the single season occupancy models, the static occupancy models. So we've already had two Toolbox seminars on the single season, the classical occupancy models, but I thought it's important for me to just cover the basics of that, the basic ideas of those models again quickly. So those of you who have been to all the Toolbox seminars are going to recognize some of the slides, but we are going to move on to the dynamic models very, very quickly. Okay, so yeah, so back here. So the basic idea is that we want to estimate occupancy, the proportion of sites that is occupied by a particular species. And occupancy, if you knew where the species occurs, so yellow here means the site is occupied, white means the site is not occupied. If we knew which sites were occupied, then occupancy would just be the proportion of occupied sites. And we could model variation in occupancy using any model that's suitable for binary data, like, for example, logistic regression. But the reality is that whenever we go and sample in a landscape, we are going to miss the species in many places. So there's an observation process. Detectability is not perfect. And so a lot of cells that are actually occupied, if you go once, you're not going to find the species simply because you overlooked it, not because it was not there. So the basic idea behind occupancy models is that we go multiple times, or we in some way have repeated samples from the same sites, and then that gives us some information on the observation process, and with that we can infer what the true occupancy probability is. So you can see here from this plot immediately two main assumptions. The first one is closure. So the occupancy status of a grid cell doesn't change. A grid cell is either occupied or not. And if you go repeatedly when you don't see it, so if you see the species once and then not the next time, you know you've overlooked it because of the assumption of that the occupancy status doesn't change. And that's quite critical information. That's how we infer the detection probability. The other critical assumption is that there are no false detections. So that means we are not going to get a detection from a site where the species actually doesn't occur. So for example, if there's a chance for species misidentification, you might get false detections, and that's a problem for these models. So the basic models assume no false detections, and that's an important assumption as well. Okay, so with the dynamic occupancy models, just to jump ahead a little bit, we are mostly, the main aim is to relax that closure assumption. So we are going to make that assumption in a less restrictive way, as you're going to see in a little while. Okay, so here still back to the normal single season occupancy model. So the idea is that we have a biological process, and And what we see is obviously, hopefully related to the biological process, but it's not exactly what we are interested in because we have that observation process going on. So it's like a filtered version of what is truly there. And so the basic occupancy model works like this. So we've got, it's a hierarchical model. We've got two layers. We've got set, that's the true occupancy status. That's either 1 if the site is occupied or 0 if it's not occupied. And that follows a Bernoulli distribution. So Bernoulli distribution is just a coin flip with a probability phi. So phi is the occupancy probability, which can vary across sites. And then, so that's not directly observed, but what we observe are these, the y's, so that's 1, 0 also, if a species was seen or not, and so that's indexed by I site, but also survey. So because we go multiple times, we have J surveys. And that again follows a Bernoulli distribution with probability Pij, so that's the detection probability times set. And we multiply by set to ensure that it's 0 if the species is not there, right? If the species is not there, set is 0 and you can't detect it. Okay, so that's the basic model. Then also just to repeat, so we are usually interested in covariates. How does occupancy vary across space? And we also need to worry about how the detection probability varies across space and surveys. So we model variation in psi, the occupancy probability, using a logit. So this is like a generalized linear model. We're modeling variation in logit psi as a linear function of covariates, an intercept, and then a number of covariates, however many you want. So these, because the occupancy status doesn't vary among surveys, it only varies across sites. These covariates here are site level covariates, so that means they don't change from time to time when you go. So for example, this could be vegetation cover. If you go multiple times, that's always the same thing. So those are site level covariates. For the detection process, we can also have site level covariates. So for example, vegetation cover might affect your detection probability, but then we can also have so-called survey-specific covariates. So those are things that change from one survey to the next. Like for example, the amount of effort you spent, temperature on the day that you did the survey, and so on. So those vary between sites, but also from one survey to the next. And those are survey-specific covariates. I'm emphasizing that because we are going to see a third type of covariate when we move to the dynamic occupancy models. Okay, so in the previous Toolbox seminars, I used Southern Bald Ibis as an example and bird atlas data, and that's just an example where we modeled the distribution of the bald ibis using occupancy models and spatial covariates. Okay, but now I want to move on to the dynamic occupancy models. So those are really just an extension of the single season occupancy models, and the main thing is that they are relaxing that closure assumption. So the idea is now that closure is still valid within what's called a season. Now a season could be whatever you want it to be, a month, a year, whatever. It's just sort of, that's a generic name in the occupancy literature. And within one season, we also have repeated surveys. So it's like a single season occupancy model. And we assume closure. We assume that the species doesn't disappear or appear while you're doing these surveys. But then from one season to the next, we allow for extinction and colonisation to happen. So in that way, the closure assumption is relaxed, so we are allowing for changes in the occupancy status from one season to the next. So season or year or month, whatever that time period is. Okay, so the model is quite similar to what we saw before. So we still have the set, the true occupancy status, which is 1 if the species is there and 0 if it's not there. Now that's indexed by I, the site, but also by time. So that's season. So we've got season 1, season 2, season up to season T. And that again follows a Bernoulli distribution with probability psi IT. So now the psi, the occupancy probability, can also vary across sites and over time. But what we are actually seeing are the Y's, so that's the observations, detections, non-detections, and they are now indexed by I, T, and J. So remember before it was just I and J, site and survey. So now we are also indexing by time. So it means we've got repeated surveys within each season. And that follows a Bernoulli distribution very similar to what we had before, with the detection probability times set. So this should actually be set IT. So there should also be a T subscript here. Okay, so that's so far looks very similar to what we had. But now the thing is that these occupancy probabilities in the first season of your study, we modeled the occupancy probabilities very similar to what we had before as a function of site level covariates. But then in the next season or future seasons, the occupancy probability is modeled as a function of the previous occupancy status and extinction and colonisation probabilities. So we've got set, if the grid cell is occupied, it can stay occupied with probability 1 minus epsilon, where epsilon stands for extinction probability. And if a site is not occupied, it can become occupied with probability gamma, which stands for colonisation probability. So for all t greater than 1, we calculate that occupancy probability as a function of the previous occupancy status and colonisation and extinction. So the cool thing about that is that now we've got a model where the parameters are extinction and colonisation, so the dynamic parts, aspects of the species distribution, and we can now also examine variation in those dynamic parts of the model. And if you think about it, extinction and colonisation are really important processes, and with this model we can directly estimate those and test hypotheses about what is affecting these processes. Okay, so just before we move on, so we're going to look at covariates quite a bit more, but the third set of covariates now that we can have is so-called yearly site covariates or season-specific site covariates. So they are constant within a site across the different surveys of a season, but then they can change to the next, from one season to the next. And examples of that would be maybe habitat that's sort of changing from one year to the next, or sort of processes that are happening more slowly. And occupancy and extinction and colonisation can be a function of those. Okay, so I'm going to show you an example with a simulated data set. Now, simulations are convenient because we know what the truth is, but obviously it's not as exciting as having a real data set. So I simulated data for 250 sites, 5 seasons, and 2 surveys per season. So you can see the part of the data here. So we've got 10 surveys essentially. Each season we have 2, so survey 1 and survey 2 were done in season 1. So that's, we are going to assume closure over that period, and then that's the next season here with surveys 3 and 4 and so on, and the last one are 9 and 10. So in the simulations I used an initial occupancy probability of 0.6 and then variable extinction and colonisation probabilities and also variable detection probabilities. You can see the true occupancy, true proportion of occupied sites starts at 0.6 and then declines a bit. What we actually observe, so if we didn't account for the observation process, we would observe the species at a lot fewer sites because the detection probability is less than 1. And you can see that the dotted line here is the uncorrected observed occupancy. Okay, so the data need to be in this type of format. So it's like a long matrix where the different surveys are just in the different seasons are just pasted together. You can see the dimension of this array or this matrix is 250 rows. So that's for the sites down the rows, and 10 columns. That's the surveys. Okay, and maybe just to go one step back quickly. So I just want to emphasize the parameters that we are going to estimate are the initial occupancy probability here, and then extinction and colonisation, and then also the detection probability. So it's 4 sets of parameters that we are interested in. Okay, so in the unmarked package in R, there are functions that fit these occupancy models and also multi-season occupancy models. So we first need to get the data into the correct format, and unmarked has got a number of helper functions. So one of them is called unmarked multi-frame. So this turns our data into the correct format that we need to pass it to the function that fits the models. And what this function needs is it needs to know what the survey histories are. So in our case, that was a YY matrix. And then yearly site covariates. So in my case now, this is just year. So it's just year 1, 2, 3, 4, 5, because I want to be able to model the extinction and colonisation probability as a function of year, so that they can vary from year to year. But here, if we had observation survey-specific covariates, those are called observation covariates in unmarked, and you could also have site covariates. And David is going to show you an example where he's using all these different types of covariates. Then we also need to tell unmarked how many primary occasions we have, so that's how many seasons. We have 5 in this case, and then unmarked. And then this function here turns these data into an unmarked object, and unmarked frame object it's called. So you can see a summary here. We can see we've got 250 sites. So you always need to check that things are correct. Maximum number of observations per site, 10. Number of primary survey periods, 5. So it all looks correct. Number of secondary survey periods. So with that I mean number of surveys within a primary, within a season. Looks correct. Sites with at least 1 detection. So this gives you a chance to just quickly double check whether things are correct. Then here a tabulation of observations. So in our case, we had 258 detections and 2,242 non-detections. So it also again gives you an option to quickly check that things are correct. Then it gives us a summary of the covariates. In our case, we only have 1 called year, and it's a factor. So you can see it's a factor here. We've got 250 observations in year 1, year 2, 3, 4, 5. So that means those are the 250 sites, and that's the dimension of our covariates. Right. Okay, so with that we are ready to fit a multi-season occupancy model. The function is called colonised for colonisation extinction, I suppose, and it has 4 parts. So these are the 4 sets of parameters that I mentioned a few slides ago. So the first one, psi formula. So this is the formula for modeling initial occupancy, and the formula works a bit similar to like if you're using linear models or most other models in R. So it's got that tilde operator here, and then to the right-hand side of tilde, you put the covariates you want on this part of the model. So in this case here, I'm just going to model initial occupancy as constant, Then we've got the gamma, so that's the colonisation probability. I'm going to model this as constant. And then extinction probability, also constant in this model, and detection probability, which I'm also going to leave constant. So this is the simplest multi-season model you can fit. You're only going to estimate 4 parameters: initial occupancy, colonisation probability, extinction probability, and detection probability. When we do that, and then pass the output to the summary function, we get the parameter estimate. So here, this is the initial occupancy, colonisation, extinction, and detection. You can see here the initial occupancy probability. Initial occupancy is estimated at minus 0.00337. Now, why negative? Well, this is on the logit scale. So remember, we model variation on the logit scale, and that's true for all 4 parameter sets in this particular model, or in this modeling approach. So you can see here, because we kept all parameters constant, we just have one estimate for each of these parameters. Okay, so now so we see that initial occupancy was estimated at minus 0.0034. So that's the logit of it. What is psi? So it probably should be close to 0.6, right? Because that's what I used in my simulation. Well, so this is, it's just, you just need, this is on the logit scale, so you just need to use the inverse logit to get the occupancy probability, initial occupancy probability. So inverse logit is here, and that's just how you do it in R. And we get 0.5 initial occupancy, which is not too far away from 0.6. It's not exactly that, but the model is different to what I used to simulate, so I wouldn't expect this to be exactly the same. And anyway, there's some stochasticity in here because I simulated the data. Okay, so 0.5. Now, it's always good to double check things by hand. Make sure you understand exactly how these things are calculated. But unmarked does have a convenience function. So this one called back transform. And what you need to do is give it the model output, so the model fit. And then you need to tell it which parameter you want to be back transformed. So this, in this case here, because we have a constant parameters, it's really just the inverse logit. And you can see here you're getting an estimate of 0.499, which is the same as we got by hand, but it also gives us a standard error. And then we can use the confidence function to get the confidence interval around it. Okay, so that's quite convenient. Just here quickly, the different parts of the model are, as we should expect, psi, then colonisation, extinction, and detection. And we can apply that back transform function on all these types of parameters. Okay, so but now, what about, so this is initial occupancy. And I told you that occupancy probability in subsequent years are a function, are derived parameters. They are a function of the earlier occupancy and extinction and colonisation, like this. So this is the formula we saw earlier. Now, I want to know what those occupancy probabilities are. So you could go in and pretty much by hand calculate in an iterative way what these occupancy probabilities are. But unmarked, again, does it for us. So I first just want to look at what the back transformed extinction and colonisation probabilities are. You can see extinction is higher than colonisation. And there's this one slot in the output object, in the fitted object model fit, called projected.mean. And that gives us occupancy probabilities in year 1, 2, 3, 4, 5. And then unoccupied, so that's just the inverse of it, 1 minus. Okay, you can see we are seeing a decline in occupancy from about 50% to 22%, and that's kind of expected because our extinction probability is bigger than our colonisation probability, right? So that means a site is more likely to go extinct than to be colonised. Now, do you think that decline would that continue forever, or is it going to balance at some point? So this, you would think, well, the extinction rate is bigger than the colonisation probability, so you might think eventually the species is going to go extinct. But actually, if you think about it, and that's a little bit the tricky thing about interpreting these probabilities. If you think about it, an equilibrium, so if these probabilities are constant, there's going to be an equilibrium at the point where the same number of sites go extinct as colonized. So, for example, you've got each year 10 sites going extinct and 10 getting colonized. Now, because these are probabilities, if you have fewer and fewer sites are occupied, even with a higher extinction probability, fewer and fewer sites are going to go extinct. And there are many more sites now unoccupied, so many more sites that can get colonized. And even with a smaller colonisation probability, you will at some point get the same number of sites going extinct and being colonized. So actually, it turns out with constant gamma and epsilon, the occupancy across the landscape is heading for an equilibrium that's given by gamma divided by gamma plus epsilon. And in our case, that would be 0.22. So we are actually, after 5 years, quite close to the equilibrium that we are expecting if extinction and colonisation remains constant. So you can see here in orange that's the fitted model. The white is again truth, and you can see we are relatively close, even though I told you that the model isn't actually what I use to simulate the data. Okay, so now on these derived parameters, I also want to get an uncertainty bound, a confidence interval. Now here, Unmarked has got a bootstrap routine. It's called non-par boot. You give it the model fit. You tell it how many iterations you want. So 1,000 is probably, if this is for a publication or thesis chapter, 1,000 is probably good. But this takes a while. So if you pass these to the non-par boot function, it does a non-parametric bootstrap and adds output to our original model fit. So now we've got it there, and we can now look at the standard errors here. So these were the projected occupancy probabilities that we saw earlier, but now there's also a slot M0 at projected.mean.bsse, and that gives us the standard error, bootstrap standard errors for each of these probabilities. Okay, and then we can draw the confidence intervals. Right, so now, so this was a very basic model. So now I'm going to fit the model that's much closer to the one that I used to simulate the data originally, namely with year-specific colonisation, extinction, and detection probabilities. And you can see here in pink, that's the model fit for model M1 and confidence intervals. So you can see, I'm not quite sure which one actually does fit better, but it does look like the first model that we fitted is biased a bit low, whereas this one is just very imprecise. So it's probably a little bit ambitious to try to estimate so many parameters. So now that means we are going to have a different colonisation probability for each year, different extinction probability, and this different detection probability. But so what we want to do now is want to know which of these two models fits better to the data, or I should maybe say which model is a better model in terms of explaining the structure in the data. And you might be tempted to use the AIC function, like with linear models or GLMs or anything. Turns out that for some reason this doesn't work because there's no method for log leak to extract the log likelihood from an unmarked fit. Instead, unmarked has got its own function to do model selection. So we first pull all the different models into a list. So that's a function fit list, preparing that list. In our case, it's just 2 models, and I'm giving them a name. And then using that mod cell function, which gives me the model selection table. So you can see here, in this case, the second model that we fitted is a lot better in terms of AIC compared to the first, the constant model. And David is going to show you a bit more about model selection in a moment. Okay, are there any questions so far? All fine? Yeah, so I've got just one more slide here with some key references. So the initial publication that introduced the dynamic occupancy models was McKenzie et al. 2003. Then here by Linda Ware is a very interesting, very detailed application to frog occupancy dynamics. The unmarked package was introduced in this paper here, and then there are also some really good vignettes that come with the package. So there's one particularly for dynamic occupancy models. And here Bailey et al. 2014. So this is just a very concise and nice overview of the occupancy models. And obviously McKenzie et al. The Bible of occupancy models, the occupancy book. Okay, and with that, I'll hand over to David, who is going to take you through an example.
Right. Thanks, Russ. I think you made my life much easier. So I'll go straight into what I did for yellow-breasted, which is a threatened species. Although Russ said mine is more exciting, I think his is exciting because it's got an opportunity to simulate data. In my case, I have to do the real data. Oh, yeah, thank you. Now, when you're dealing with with actual real data and rare species, you might have ugly models and you might not be able to convince your audience. But I thank rest because the other part was well explained. Right, let's see if I can maneuver this. Yeah, good. Okay, most of you probably know Yungula, but if you don't, it's a mountainous area. We impose a grid of 500 by 500 meters throughout the entire area. But this area is rocky, so we choose only pentads that are 70% or more grass. This is where we're going to survey for these species. Many birds here undertake altitudinal migration or international migration. As a result, for multi-season modeling, we only chose summer, where we can confidently say our species will be there, or the grass will be dry. Won't be dry. We'll be able to see it because it will be breeding. Although I must say, searching for yellow-breasted, it's a mission, right? You'll see with some other slides. So we have 4 seasons. Our 4 seasons are actually months, from November up to February. And for each, I had to do 3 replicates, recording presence and absence of this species. And in total, I have 19 plots. from where I was searching for these birds. Not only that, I was also recording vegetation, and Russ has already explained to you what some of the covariates are called, but I'll quickly take you through the data format, which is the Y, is the occupancy data, which is detection history. If you found it, it's 1. If you haven't found it, it's 0 per visit. Site-specific covariates. In this case, it's either ESCOM land or private land, so it doesn't change. Like Red said earlier, OPSCOPs, these were much more interesting. I think Res for agreeing with me, or at least approving what I was doing, because I said, well, weather influences species that we see. And by weather, I mean hot, cloudy, and cool, the combination of those. I made a suggestion to Res that let's call this observability covariate, and he said yes. Then it worked for us. Then this OPCOPS is a combination of the weather condition at that particular pen at the time you're surveying. Yearly site covariates, you go once in November to record vegetation, but the 3 other visits, you are not recording vegetation. Rest has already said that. I think I'm done there. I can go to next. Right. So with yellow-breasted, which is not such an obvious, you can see it's beautiful, but it's not so obvious to see it. Then the NAs, it's where I didn't go, probably because it was rainy and slippery, and therefore I didn't survey those plots. Right, I don't know what I've written there. I hope you can read. Okay, some will argue that this is a lawn claw, but in fact it's not. It's not a lawn claw. Lawn claw doesn't patch on rock. So why did yellow-breasted patch on rock? I wanted to take a picture of it, and I was in a car, so I forced it to climb on the rock temporarily. So please, it's not a lawn claw. Right. Right. This is the same function which Res has talked about. Observability that I told you about, which is really about weather conditions. We have 4 numpram is a function which is 4 repeat surveys. All this Res explained to you. I'm not going to waste time on explaining them, but this is what we get about the observability of yellow-breasted pipit, which means we have much more higher chances of seeing it around this value, and these are what are they called? Confidence intervals. Yes. Good. Next. Now that we have seen how the observability probability behaves like for this particular species, now we want to fit few models. The first one is a null model. This is occupancy, the first one. This is colonisation. This is extinction. And the last one again is detection. Everything is constant other than observability for that first model. The second model, this one is grass height. How does grass height affect our plots to be either colonized or to go extinct? And this is grass cover. There's a paper that we wrote about this. If you want to read in more detail, you can go and read the paper. But now again we're using that function which Res explained earlier, where we want to know which model is the best. So in this case, the best model is the model with cover. And it is the best model. It's got a, where the null model is greater than P, it's greater than 2. So in this case, we want to go further and explore this model because it's the best model in this case. Right. This is what I said to you earlier, that when you're dealing with simulated data, you can show much more nicer graphs. But if you're dealing with real data, it's not so easy. You might end up having horrible graphs, but that's actually how the world works. I remember when I was working, fumbling around this PowerPoint in the middle of the night, and Res, we're talking in cyberspace, and he said, "Oh no, Dave, we have actually scaled our covariates, which is we selected between -2 and 2. That's why you see -2 here. So you can see that in this particular case, or perhaps I should start by explaining that colonisation, its ability of an occupied site to be occupied. Is that correct? Yes, yes, yes. So you see, in terms of grass cover, you can see that the more it's getting, the grass cover increases the chances of probability of colonization is not so good. And you can see that it comes down here very sharply. In the simulated data, would have a much nicer decline, but unfortunately in this case, but this is the real data. Right, this could be the next slide before the last, right? Our conclusion, okay, in this case now is the grass cover. Again, colonization and extinction of yellow-breasted pipit. It's negatively affected by both increasing grass cover. Extinction and colonization. It's affected by increasing grass cover. But I think our Bayesian approach, which we did in this paper, I think it shows much more interesting, convincing results than a marked. But you can go and paper and argue and give us feedback. I think the reason why we are getting a little not so good, not so interesting graphs is because, like I said earlier, we are dealing with the real data. This is becoming true if you're dealing with a rare species like yellow-breasted, as I did say. Right, the last slide, right? Now, this has nothing to do with occupancy model. I simply want to thank you and say, if you're going to work on rare species, you must know the challenges of ability to detect species is quite a problem. Many field guides will tell you that no, in winter you won't find this bird up there, but we know that it is there. Here are the pictures. You can see that I think this was taken in September. You see, it looks like just another African crasswell pipit. You have to know what you're looking for. Lucky enough, this bird decided to turn around, and then I could see the yellow throat, and that is in June.